Hey y'all, I'm the group lead for group 4 for the Clapeyron experiment. The introduction, Clapeyron equation represents an important relation between the saturation pressure and temperature, change in enthalpy associated with the change of phase and the specific volumes of the two phases. Determining a change in a property that cannot be directly measured using measurements of pressure and temperature. And this is what the equation does. It measures enthalpy in our case. Our objective is to determine the latent heat of vaporization for water by utilizing the Clapeyron equation over a range of temperatures and pressures. And we want to verify our results using our steam tables. Theory, the Clapeyron equation is the derivative of the saturated pressure equation with respect to temperature, which is equal to your entropy of your vapor phase over the specific volume of your vapor phase, which is equal to the enthalpy of your vapor phase over temperature times the specific volume of your vapor phase. As you can see, Psat is our saturation pressure. T is the saturation temperature. HFG is our latent heat of vaporization. VFG is our specific volume. And we use the ideal gas equation for an approximation of a specific volume, so we don't have to rely on the tables. Our apparatus is as follows. I have a 100 or 1,000 milliliter flask with a rubber stop of a hot plate, type K thermocouple, a pressure transducer, mechanical pressure gauge, air bleed valve, vacuum control valve, centrifugal pump, and our water reservoir, and our computer with our data acquisition system. Procedures as follows. The acquisition system, we start the software, we verify the thermocouple and pressure transducer are connected to the computer. We check to see that the sampling rate is correct. We want to record a sample approximately every 2.5 seconds. And we want to verify that the thermocouple and pressure transducer are working properly. At the beginning, before the experiment begins, they should report ambient conditions. Preparation, we want to fill our 1,000 milliliter flask with approximately 2 inches of water and set it on the hot plate. We want to add boiling beads as instructed by our TA. The boiling beads serve a purpose to make the water boil more calmly. It reduces the bubbles and erratic behavior. Then we want to place the thermocouple so the tip is about 3/4 of an inch below surface of the water. Then we close our vacuum control valve and open the air bleed valve, and we turn on our hydraulic vacuum pump, which was the centrifugal pump on the previous slide. After the pump is on, we want to open our vacuum control valve to verify that air is being drawn into the system. Then we want to perform a leak test. We close the air bleed valve and check to see if the stopper is tight in the opening of the flask. It should be sucked down into it. Monitor the pressure. When it is very low, close the vacuum control valve and turn off the pump. The pressure should remain near 0 if there are no leaks. Then after our leak test, we perform our experiment. So we draw the vacuum like described in the previous slide. Then we turn on the hot plate to its highest setting. We want to leave our vacuum control valve open and then begin logging data when the water begins to boil. Then we want to slowly close the control valve so that the pressure rises back to atmospheric pressure. And we open the air bleed valve so we avoid any pressure buildup. Once the water reaches a rolling boil at atmospheric pressure, we stop logging data. And we note the pressure and temperature at this point for a calibration test later on. And our shutdown procedure is to turn everything off and allow the beaker and hot plate to cool before handling. Expected results, this is a pressure versus temperature diagram pulled from the steam tables in the back of our thermo book for the data. And you can see it follows a 3rd or 4th order polynomial fit. We use a 4th order fit for further calculations. So this is our fourth order fit equation as seen on the previous slide. We used a starting temperature of 15 degrees Celsius, I chose. We use our ideal gas constant of 0.4615 in our equation down here. All right, and at 15 degrees Celsius, we find a saturation pressure of 5.7878 kilopascals. And then taking the derivative of the PSAT equation with respect to temperature, we get this. And again, evaluating at 15 degrees C, we get negative 0.970 kilopascals per Kelvin. Plugging those values into our equation, we get enthalpy, or a latent heat of vaporization, of negative 6,419.27. So you can see we have a temperature of 15, 100, and 300 degrees Celsius, which pressures correspond to these. Our calculated latent heat of vaporization, negative 6,419, 2,403, and 2,157. And then our tabulated from our steam tables of 2465.93, 2257.03, 1404.93. These are all in kilojoules per kilogram. The calculated latent heat is for 15 degrees is way different than our tabulated. This can be due to a number of things. My thought is that it's due to the curve fit used. It's a fourth order fit, but you saw that R squared was 1, so it perfectly matches the data and it tends to steer it in a direction that doesn't actually follow. So I'm not sure why exactly the latent heat is negative, because it can't be, but that's how it came out in the equation. So our latent heat of vaporization should fall as temperature rises. Our measure values should follow the trend associated with the curve from the steam tables. Some sources of uncertainty: the location of the thermocouple in the flask, not submerged enough, or it's touching the flask wall, which would throw off the reading, and the rate at which the valves are closed. Closing that vacuum control valve too quickly, or opening it too quickly, and all that is could throw off the boil, and you don't want that if you want accurate results. References: the lab manual and the thermo textbook. Thanks, y'all.